Series equivalents. There are four series characteristics to equivalence. And we ask the following questions. How do resistors add in series? How do currents add in series? How do voltages add in series? And then finally, we ask, how do voltage and current sources add in series? We have to answer those four questions in order to understand completely what a series equivalent is. So the first one I'm going to go after is going to be series resistances. The resistance equation tell us how resistors behave geometrically. In series circuit, adding elements in series effectively increases length. So when I look at the resistance equation, we could see that there's the resistivity, the length divided by the area. We see here that resistance depends on length. So it's directly proportional to the length. In other words, the resistance goes by the length parameter. So adding resistors in series is equivalent to increasing the effective length of resistance. So picture-wise, what does this mean? So imagine that we have a series of resistors. So I'm going to go, here's 1, 2, and then I'm going to have, let's say, this many resistors here. So I'm going to have R1, R2, and this will be Rn. So the effective length, by adding them in series, I effectively create one resistor that's longer. So in other words, these R series resistors is equivalent to adding all of the resistors into a longer resistance. In other words, a series of resistors can be replaced by a single equivalent resistor. Called R series, where of course R series is the sum of all of these resistors. So picture-wise, how do we draw this? Or circuit-wise, if a branch of a circuit is isolated and has multiple resistors in series, then we have this scenario here. So I could imagine that I have something like this, where I'm going to have and let's say that I only have 3 resistors here. But if I do this, you could imagine that I have some complicated circuit here, right? I've been able to isolate this branch from the rest of the circuit. So I could call this resistor 1, 2, 3. Then the equivalent, maybe I should say series equivalent, can then take on this form. How about if I copy this? I can replace this circuit mathematically and conceptually by one single resistor. And this one single resistor is then R series, which is then R1 plus R2 plus R3. That turns out to be a very powerful, powerful way of looking at the world. Now, let's go to the next one. 2. Now we want to talk about series currents. All series elements can only have one path to move through. As a consequence, or therefore, all series resistors must have the same current. So again, if I take these circuits right here, and I'm just going to modify these, but it's the same idea because we're talking about the same circuit here. So what we're seeing here is that I could imagine that I have a branch current that's coming in. Now, each of these resistors has one current that flows through them. So when I look at this series resistance, because all of these currents are exactly the same, I only see one current flowing through all these resistors. It's the branch current. And therefore, this branch current must be the same as I1, which has to be the same as I2, which has to be the same as I3. So they all must have the same current. So the next thing that we want to talk about is we need to talk about voltages. So now we're at 3. We're going to talk about series voltages. What we know here is that series elements always divide the voltages. And this is where we talked about the fundamentals of series circuits here. So series elements always divide the voltages, and there are two ways to visualize this. The first one, which is the one you're taught in physics 4B, is KVL. And so when you look at KVL, it says that the voltage of the branch must be equal to the sum of the individual voltages. A much more powerful way of doing this in reduction circuits is something called the voltage divider rule, which follows an acronym of VDR. And VDR reads something like this. It says that the voltage of the nth resistor is equal to, so it's divided by the series resistance divided into the nth resistor times the branch voltage. The vast majority of the time, okay, so this is a big one right here. And I should probably call this a warning. In general, with reduction circuits, always assume VDR is used to calculate voltages. KVL should be the last thing that you should think about. In fact, if you're using KVL in general, that means you didn't see the circuit. Okay, you didn't see the circuit. So let's look at this thing. So here's what we know. What we want to do here is to show you that VDR is a valid theorem in circuits. Remember, it's still part of KVL and Ohm's law. So to derive VDR, one uses the series equivalent circuit. So if I come all the way back up here, we've already done this. So let me grab this and bring it with me. So I'm going to put this in here. I'm going to paste this. So now the thing that I'm going to do different here is that now I'm going to add a voltage of the branch. So what I'm really seeing here is that I'm seeing this. I have a voltage drop across the whole branch, and I'm going to call that V branch. And of course, over here, this is going to be V branch as well. But because each of these circuits has a voltage drop, then that means I also have a little voltage drop. 1, 2, and 3 across each element. These two circuits must be identical. So now let's apply, the behavior of the current in Ohm's law. So then using that I source and all of these currents are the same, and applying Ohm's law, here's what we find. We find that the current, regardless of which current it is always going to be the same constant. So that means here, this could be I1, this could be I2, but this could also be, and in this case, I'm going to say instead of just having 3, I'm going to go all the way to n, because that's what we mean by series. But now, if I then use Ohm's law, what do we see here? By the way, I should have had source right there. So what this tells me here is that I now have this. I have I source, which is the same as the voltage of the branch divided by R series must also equal IN, which then means it has to be the voltage of the nth resistor divided by the resistance of the nth resistor. So now if I rearrange the voltages, so if I rearrange only the voltages, here's where we end up here. We find out that Vn is the same as R series divided by Rn times V branch. Once again, this is our equation for the voltage divider rule, right? So this guy is the voltage divider rule, which we define as VDR. A very, very powerful equation and extremely, extremely useful. So let's look at this thing. So physically, what does VDR tell us? Well, I could think of two things. The first thing, and probably the most useful, is that the voltage drop across a resistor is directly proportional to its resistance. In other words, the voltage of N is directly proportional to the resistance. So in other words, a larger or higher resistance value immediately tells you that you have a larger voltage drop across that resistor. In other words, because Rn is so large, we would expect it to have a higher voltage drop. Now, if I have a smaller resistance, then I'm going to have a smaller voltage drop. In other words, because I have a smaller voltage or smaller resistance, I expect a smaller drop. So right away, just by looking at a circuit, you're going to know that right away. And the other thing here is that VDR has the ratio that reads like this. It says that it's R series divided into Rn. What this really is it tells us about the percentage of voltage drop this tells us the percentage of voltage drop across a series resistance. So that's really a proportionality. Okay, that's VDR. And I won't go into, well, maybe I should talk about KVL. Let's look, but we've already talked about KVL. So I think I'm not going to talk about KVL. Okay, so then the next thing I'm going to do here is that we want to do the fourth thing, and we want to talk about series power supplies. So what we want to do here is that we have to separate out both of these guys. That means voltages and current sources. So let's first talk about series voltage sources. And what I'm going to say here is that series voltage sources must add together. And the way we'll do this is that we'll consider a circuit and then we'll go from there. So I want to see if I still have a circuit here. So yes. You know what? I'm gonna not use that. So consider this branch of a circuit. So what I'm gonna have here is that I'm gonna have my sub-circuit here, right? Here's my sub-circuit. And what I'm gonna do here is that I'm gonna arbitrarily draw an odd number of sources. So in this branch, I'm gonna have a source here, here, and then I'm gonna have another source here. So the polarity of these guys is just arbitrary. So I'll make this plus minus, I'll make this minus plus, and I'll make this minus plus. And so I'll just start labeling these guys as calling this guy source V1. This one's force V2. And then this guy I'm going to call Vn because there's n sources here. But one of the things that I know here is that this is still the voltage of the branch. So I'm going to want to copy this because I'm going to need this. Now, what I want to do here is that I want to apply KVL in the, how about clockwise direction. In other words, I'm going to come in here and I'm going to pick my direction along this loop going like that. So here I'm going to apply KVL going around a loop in the clockwise direction. So if I look at this thing, this is what KVL tells me. What it tells me here is that I'm going to get a positive V1. And if I go to the green, I see I get a negative green. And then I have a series of sources. And then I get to the blue, and you could see that I encounter a blue symbol. And if I go all the way around, you could see that this guy is V branch. So when I look at this thing, what you're seeing here is the equivalent series voltage is this guy. It's going to be so V series must be the same as V branch. And then this guy is then going to be plus V1 minus V2, and then adding all of the sources, I'm going to get minus Vn. So what this is really telling us is it's telling us this. One can replace all these voltage sources with its equivalent. So if I do what we did before, I have this circuit. Now I can, if I look at its series equivalent, I can really just have only one of these guys. I only have one source. And this one source is this guy right here. And so I don't have to worry about that. The only thing I worry about is now this is V branch. And we already know that V branch is this quantity of things. So let me bring it down. So if I delete that and I just paste this guy in here, that's V branch right there. So in other words, this is the equivalent. So the series equivalent is that one voltage source right there. Again, that is really, really powerful. So now let's look at current sources. Series current sources must all have the same value. So let's put in our circuit again, but now we're going to replace the voltage sources with current sources. So if I look at my circuit here, oh, that's not what I want. Let me delete that. Let me grab this guy again. So the only thing I'm going to do is that I'm going to replace all of these with current sources instead. And I don't care about the voltage now. I only care about the branch current. So that means here is the branch current. It's coming from that thing here. And so when you're seeing it, I could then come in and arbitrarily put in that I1, let's say, points up. The green points down. And the blue, let's say, points up this time. Now, if we apply KCL at each node, this is what has to happen. So for example, if I look at the top node right there, let's call that node A, then what we're seeing here is that that node A tells me that the current coming in and the current coming out are opposite in direction. So if I look at node A, you're seeing that this node tells us that the branch current is coming in and the current I1 is coming in like this. That immediately tells us from KCL that I branch must equal the negative of I1. So in other words, this current must be the negative of that current. What happens if I apply this guy here? If I look at node B, that tells me that these currents are both moving out. So again, this tells us here that I1 must equal the negative of I2. But wait a minute, I1 is the same as minus I branch. So that immediately tells us that I branch must be the same as I2. And if I focus, let's say, on node C here, let's assume that the only source is this I2 and IN, then this is the source at node C here. Then if I look at that node, I'm going to see that I have the green like this coming in, and I have the blue coming in like this. So again, if I start to apply KCL at this node, that tells me then I2 must be the same as negative IN. But we already know that I2 is the same as I branch. So if I now put this all together, we see here is that I branch must equal negative I1, which then must equal positive I2, which then equals minus IN. So all of these currents must be the same, or else they violate KCL. So let's say a couple of words here. So if all of the series current sources, no, I should not have said if. That means all of the series current sources must have the same current values. Otherwise, they would violate KCL. Excuse me. Again, what does this mean? What does this all mean? What I mean by that is that what if the current sources did not have the same value? So if series current sources do not have the same currents, the current sources would discharge slash damage the power supplies. Until they all have the same current values. And this is typically the lowest possible value. This is hard to imagine. It really is hard to imagine. So what we want to do here is that we want to wait till voltage sources, because that will make a little bit more intuitive sense. So to finish off series equivalents, I want to go through an example and apply everything that we just used. So in this example, we want to make the branch as a series equivalent to make it easy to deal with. So here's our example. So I have a 1 ohm connected to a 6 volt connected to a 2 ohm to a 12 volt source, and then finally to a 3 ohm. Remember, this is only a branch of a complicated circuit here. So the first thing that we want to do here is that we want to use reduction. So if I look at reduction, we're going to use reduction, but because all of these are in series, we can draw them. We can move them around. And so what I'm going to do here is that I'm going to copy this and try to paste this over here to try to move quicker. So here's our branch. So the first thing I'm going to do is I'm going to move all of the resistors. So I'm going to have 3 resistors in series, and I could move them right past the power supplies. And then I'm going to have my power supplies, which then I'm going to combine into this shape right here. So now you could see here that I have a 1, a 2, and a 3 ohm resistor. And then over here, I'm going to have my 6 volts. And this guy is going to be my 12 volt source. So you could see is that the first thing that I did here is that I grouped all of the resistors together. And then the next thing that I did is that I grouped all of the sources together. So now if I want to do this, I could now simplify the circuit with 1 resistor and 1 voltage source. So now if I look at the same thing here, let's see if I could put this right here. So what is it that I know here? So this now is the equivalent circuit now. So what I'm seeing here is that I really have one resistor and I have one source. And when I see this, I could see that V branch here, look at the sign here, the 12 volt is bigger. So then this is I'm going to change my polarity to be for the 12 volt. So this is going to be positive 12 minus 6. So I'm going to say this is 6 volts. Therefore, the polarity of this voltage then goes like that. And so if then that node right here, this node right here tells me that this guy has to be 6 volts. And then because grounds are arbitrary, I'm going to pick my ground right here. And I'm going to choose my ground to be 0 volts right there. So what you're seeing here is that if I look at my my branch resistance, well, since they're all in series, then this is going to be 1 plus 2 plus 3. So this is a 6 ohm resistor. So now I have my I branch that would then go into that circuit right there. So now we can apply Ohm's law to figure out this current here. So let's look at some of the details here. So if I look at that effective source here, so the series equivalent current is calculated using Ohm's law. In other words, I branch is then going to be V branch divided by R branch. And in our case, that means that this will be 6 volts divided by 6 ohm. So that's going to be 1 amp. So that means each of these 1 resistors will have the same current as the branch. No surprise. We expected that to be the case. Okay. Now, if I had the same circuit that we have over here, we can redraw the circuit. Now, let's say that I want more details about it. So let's apply VDR to calculate the voltages of our of the resistors. So now what I do is I modify my circuit. So here's my circuit right here. Right, this is my circuit. But now what I'm going to do here is that we know what the effective circuit is, voltage is, right? We know what that is. So in other words, I literally have one source that's V branch, which is equal to 6 volts. So now I'm going to apply VDR. Look at V1. V1 is then going to be R of the branch or R of the series divided into R1, and I should be careful. This is R1 ohm, so then this will be 6 ohm into 1 ohm times 6 amps, and so this will give me 1 volt for V1. I know what that voltage is. So if I continue along the same line, you could then see that V2 ohm is going to be V branch divided into R2 ohm. And so this will then be 2 ohm divided by 6 ohm times 6 amps. Ooh, you know what? I said amps, and you know what? I've been making a mistake. It should have been not 6 amps, it should have been 6 volts. So let me be careful here. So this should have been the voltage of the branch. And then this is 6 volts, and that's how I get 1 volt. So then if I start doing the exact same thing for the 2 ohm resistor, then you can see here is that I'm really having something like this. So then just instead of keep writing it, this will then be 2 volts, and that's the voltage of the 2 ohm. And if I get the 3 ohm, this will then be 3 ohm divided by 6 ohm times 6 volts, and that's going to give me 3 volts. What if I wanted the voltage across the 2 plus the 3 ohm resistor? Then that's going to be 6 ohm divided into 2 plus 3 ohms times 6 volts, and this would therefore be 5 volts for the voltage across the 2 ohm plus the voltage across the 3 ohm. So VDR allows you to calculate voltages without any current. And that's why it's so powerful.